Good evening, everyone. I want you to welcome Popular Astronomy members here, and we've had a busy day. We just I want to welcome you all who are coming and a few additional who have signed on Zoom. We do have some visitors here tonight. If you care to identify yourself. I'm Larry. We have Larry. Hello, everybody. Welcome. Format. Okay. Other perspective members. We have spectating members tonight. Okay.
What do you think? Okay. And I'm Laura. Meet you.
Okay.
They're friends of Janet Laura's.
Oh, good. Okay, good to have you here tonight. Let's get everybody here.
I'm Kathy.
Well,
Oh, I bet you. Oh, look here. Oh.
okay, did everybody get a chance to find the attendance list? We have a record of usage of the facility here. And for those of you online, I want to remind you to use your mute function, particularly during the presentation tonight, to avoid any background noise, even if you're not asking questions. There will be a question and answer for the end of the presentation tonight. And also, we can also use the Zoom chat. Yeah. Tonight, we will have Dr. Robert Gregory presenting the solar flares and Neptune's chemistry. Dr. Gregory is assistant professor of physical sciences at Community College, where he's taught astronomy and chemistry since 2018. Dr. Gregory received a PhD in analytical chemistry in 1983, where his research area was in optics and laser spectroscopy. After graduate school, he was employed in several industries before taking his first teaching position in 2004. Dr. Gregory's interest in astronomy has been a lifelong journey, beginning with Stargate telescope construction with his father when he was a child. He is proud to be able to share the wonder in that journey with his students. Dr. Gregory, we welcome you to the Popular Astronomy Club tonight. I will turn off my sharing so you can share your presentation tonight.
Glasses on so I don't do something silly. One.
Yeah, looks like it.
Way down here.
There we go. All right, now we're working.
You want your computer up here?
No, I'll watch it on
On a monitor there, I can see it. Yeah, you got a click? Yeah, okay.
We're good.
Yeah. Hi, everyone.
Hi.
I'm really happy to be here tonight. I'm thrilled to have been asked to do this. This research caught my eye last year. I was teaching a dual enrollment class at PV, and looking at all the interesting stuff that was popping up on the various sites. I always start my class with a run through through what's happening. So space.com and spaceweather.com and all that stuff. And this article popped up. I think it's on the Sky Telescope. I can't remember exactly which site I saw it on. I just went, wow, this is amazing, right? And it's a link between sunspots and solar activity and cloud formation on Neptune. This seemed immediately odd to me, right? I mean, Neptune is a really long way away from the sun, you know? I mean, it's just, it's an enormous thing, right? We'll just take it. There it is. All right. So this is the view of Neptune that we usually see, right? You publish a, you post a website or you put up a picture of Neptune and you want to put that at the head of your article. This is the picture you pick, right? Neptune is really pretty. It's blue, right? It's like much deeper blue than Earth is, you know, and it has a lot of stripes and everything like that. And it just looks like a blue world is kind of floating in space, right? Which it is, right? But this isn't really very realistic. In reality, the atmosphere of Neptune is a lot more dynamic. And this, so here's an example, right? This is a picture from Voyager. Voyager passed, right? With clouds. If you're going to fish islands in 1979 and you pointed at the sky, this looks very purple, right? Well, it turns out that this is a much more interesting weather and sometimes this is a set of pictures from 1994 to 2020. And this is an ultraviolet. So this it's an extreme ultraviolet. In fact, it's picking up wavelengths in the low 200s, low 100s. I think this particular filter is centered right around 30 nanometers, which is very high energy ultraviolet radiation. And so you're picking up methane very, very distinctly. That's a methane cloud. Okay, and most of the clouds in Neptune's atmosphere are in fact methane in origin. But that's a lot of variation, right? Now, one of the things you have to remember is that the year is 165 years long on Neptune, right? So it takes 165 years for Neptune to go all the way around this sun. And longer than any of us are likely to do. And that's you know, so we have to be a little careful about the conclusions we draw, but this is a lot of variation. Can I change that? Yeah. Oh, it's on my computer. Hang on, I can do it. I know how to do this.
Close it.
There we go.
Is your microphone on here? Because people are saying there's an echo.
But I could stay on the side and put the view on.
Well, I can do this. And we can turn this microphone on.
Yeah,
Thank you.
because my mic is off.
Try this.
Okay. Is that better?
Yeah, it's like, I'll mute the-
There's too many.
Not
Okay, is that better? Yeah, still got an echo. That's
Well, we can hear and then hear about that. Okay, wait a minute. I mean, we reduce the sound. Okay, let's try it again. How does that sound? Is anybody,
right.
anybody hear us online?
Can you hear us? Raise your hand and say yes.
Yes.
Okay, I see a hand up. All right, so that's good. That's good. Okay, but that participant screen is not on any of these.
Okay, that's.
Oh, yeah, you have your persistent screen, turn. Persistent screen, yeah, I can hear it.
Okay, good. All right. So where was I? This is a lot of variation, right? This is a lot of variation in clouds. And so, you know, this bears some discussion. There have been a lot there's a lot of research on, you know, seasonal variation in cloud formation and that sort of thing. Although with 165 year, seasonal variation seems to be not a very logical explanation for this, but it's been suggested. You know, Neptune is much more susceptible to cosmic rays from outside the galaxy, outside the solar system, than inner planets are, because it's at the outer reaches of the sun's magnetic field, which protects us from all of that stuff greatly. There are a lot of reasons why cloud formation on Neptune could be, in fact, much more vigorous than you might think, right? Okay. But let's back up a little bit. Let's talk a little bit about Neptune in general. So here's some basic facts, and I'm not going to run through all of these here. It's a very large planet. It's about 57 times our volume, right, in volume, which is really, really large. Its radius is almost 4 times bigger than ours is, right? That's a big planet, right? But it's only about 17 times heavier than we are, right? And that's because it's a gas giant planet, and gases don't have as much density, so you don't have as much mass there, right? All that boils down to the fact that the gravity on Neptune is almost the same as the gravity on Earth, which is like mind-blowing, right? I mean, you just don't think about it that way because it's such a huge planet, right? You think the gravity must be enormous, but it's not. Let's see, what else was in here that I thought was really kind of interesting. Its albedo, which means that how reflective it is, right, is about the same as Earth's. So its reflectivity is very similar, although obviously in different wavelengths, right? Because it's reflecting a lot deeper blue than the Earth does. All kinds of stuff like that. But the thing that I found the most interesting was this one. The solar irradiance, right? The solar irradiance is the amount of sunlight falling on the outside of the atmosphere of Neptune, okay? We'll ignore transmission through the atmosphere for the moment. Well, throughout the talk, in fact. And the thing is, Neptune is 30 astronomical units away from the sun. An astronomical unit is the distance from the Earth to the sun. So it's 30 times the distance that we are from the sun, which means that it's 1/30 squared down in the amount of light that it gets, right? So the ratio of the amount of light that strikes the Earth versus the amount of light that strikes Neptune from the sun is 0.0011, right? That's 1/1000th of the light that hits the Earth, right? So that's a really, really small amount of light, right? Which made this whole article very strange, right? You just don't, I can't wrap my brain around this, right? Okay. So if this were noonday sun on Earth, okay, if it was also noon on Neptune, this would be Neptune, okay? In fact, it would be darker than this. This is the lightest, the darkest gray I could get it to do, which was 1 out of 100, right, on the scale. So it's actually 10 times darker than that, right? Okay, so that gives you an idea how little light is actually falling on the surface of the planet, right? It's just not much, right? There we are, okay. The rest of this stuff doesn't look so strange, right? We already talked about the 30 times distance for the semi-major axis. That's the distance from the sun to the planet, right? But its orbital eccentricity is about half of ours, which means it's a more circular orbit than ours is. Its length of its day is only 16 hours, as ours is 24. Again, not terribly different, right? Its obliquity to the orbit, in other words, how much is the axis tilted, right, is almost the same. We're 23.5 roughly, and Neptune is 28, right? I mean, this is not extreme, you go to Uranus and you got way big extremities and strange things going on, right? Neptune, not so much, right? So where is all of this activity coming from, right? That's the question. So I want to talk a little bit about Neptune's atmosphere, okay? So this is a 3-panel graph of Neptune's atmosphere. The left-hand side is one that you might see in a textbook. The 2 on the right, probably never, okay? The one on the left is a graph of essentially temperature versus altitude. And altitude and pressure are related to one another. Pressure goes down as the altitude gets bigger, okay? So So if you kind of step away from the microphone right now, so, but if you start at the surface of Neptune, right, you're sitting at somewhere around 175 Kelvin. So that's the freezing point of water is at 273 Kelvin. So it's about 100 below zero Fahrenheit, Celsius. Okay, that's cold, right? Okay, very cold, but not terrible, you know, for a planet that far away from the sun. That's not that strange, right? But as you go up and down, just like on Earth, I'm going to put Earth right next to it. Okay. Maybe. Okay. There's Earth right next to it. Okay. Earth does the same thing. We start at 0 Celsius. We're about 200, or about, it's actually about 18 Celsius is the average temperature. And we drop as we go up in altitude until we hit the stratosphere. At the stratosphere, the temperature starts to go back up again, which is interesting. There's a very distinct difference between the troposphere, which is our atmosphere here next to the Earth, and the first layer of the stratosphere. There's a very distinct boundary between those two, and there's a very strong wind current that runs right along that boundary. And then once you get above that wind current, there's no turbulence. It's basically still. There's a wind current that flows, you know, around the Earth, but beyond that, nothing. Okay, so this is also very interesting, and the same thing happens on Neptune. Okay, so Neptune, you start here at a much colder temperature, but as you go up, it gets very cold. You get down here to about 60 Kelvin or so, right? So this is really cold. This is very close to absolute zero. And this is the temperature at which methane freezes. So methane crystallizes into clouds at this layer. And this layer right here is the boundary between Neptune's troposphere and its stratosphere. Okay. So the clouds that we're seeing in Neptune are forming at that layer. Okay. As you go up beyond that, it doesn't have this bump that you see here in the stratosphere. That's our ozone layer protection right there, right? And it doesn't have that. Without that ozone layer, our ultraviolet experience would be very, very different than it is today. In fact, it would be hard to imagine life on the planet without that ozone layer bump right there. Neptune doesn't have it. In fact, we're the only planet that we've found so far that has it, right? Okay. On the right are concentration graphs. Okay, the middle panel is are the species that are highest in concentration, and the one on the right are the ones that are lesser in concentration. So you have hydrogen, which is a huge component of the planet body itself. It's also a huge component of the atmosphere, and it has in the pink in this middle panel is hydrogen, and it comes here and it gets very large here, comes back down, and then drops off as altitude gets very hot. The gravity of Neptune is able to constrain hydrogen into that layer. The temperature also helps make that constraint happen. And then these two, the two blue curves, the blue and the purple curve, are forms of methane. So methane is the simplest carbohydrate. It's hydrocarbon, rather, not carbohydrate, hydrocarbon. It is also the major component in natural gas. Okay, right. So methane is very common in the solar system, and you've got two different versions of methane in those two curves. If you knock this down by about a factor of 100 in concentration size, then you get to things like ethane. Ethane is the second most popular component in natural gas. It's 2 carbons with 6 hydrogens rolling around the outside. Okay, and these two things are actually what are causing us to have this cloud layer situation. Okay, and that's the best way I can describe it for right now. We'll get into how this works in just a minute. Okay, Liz says it's often hard to understand.
When you walk over to
Yeah.
I'm going to unmute it there, and that's the microphone.
Oh, yeah. Okay. Yeah, good idea. All right. Matter. Well, I can just stand over here. Why don't I just stand over here and we'll just leave this on? Is that better, Liz?
Liz, is that better? Can you hear now? Can't hear it. Can't hear it all.
Yeah, somebody's talking over you, it looks like.
That's us.
Oh, that's us. Oh, that,
This is Catherine.
oh, we're Catherine Butterworth.
Yeah.
Wow. I am Catherine Butterworth. Yeah, right. Big K. Okay. All right, sounds better. Okay. Is that still better? I don't know. We're not getting an answer to that question.
Good.
Anybody hear us out there?
Yeah,
Yes.
some, she says, some. Okay, I don't know what to do.
Does anybody else have any problems hearing us?
It's good for me.
Back up, but you did turn it off down.
Yeah, I hang on a second here.
Yep.
I got too many controllers.
Right.
I got one for the TV here.
Yeah, see, did you want some?
Okay, say something.
Is that it? Other than that?
I think this is working. I think it's going to keep the volume.
Yeah, it's just TV down.
If somebody wants to say something on it, let us know.
Yeah.
And we can bring the volume up.
Okay, so I'm just gonna stand right here so it picks me up. And that way I can point and gesticulate and jump up and down and do all the stuff I like to do anyway. So, which is perfect, right? So these concentrations are down by about a factor of 100, is what I said, right? So these are minor components compared to hydrogen and methane, okay? So ethane's here, there's hydrogen sulfide here, that sort of thing, okay? Good. You might ask, how do we know that that's what's happening, right? And the answer to that question is, we do exactly what we do everywhere else, right? What is the farthest away that human beings have ever had a foot on the ground? The moon, right? We have never been farther away than the moon, right? We've had satellites, we've had landers on Mars, right? And that's as far away from the sun as we've ever had a lander. Right? I mean, you know, any robotic lander that can roll around or anything like that, right? I mean, we know we've not really walked very many places other than Earth, right? So what do? Well, we look at light, right? And we take light and we spread it out. And when I say light, I don't just mean visible light. I mean light in the ultraviolet, in the infrared, in the X-ray, in the radio waves, everything, right? We spread it all out, the energy. And we know from studying that which species respond to which wavelengths of light, which energies of light that are being shown, right? That's called spectroscopy. Yeah, that's my thing, right? And you know, that's where I got my degree in, and I have to admit I love it, right? And this is an example. So this is Neptune again. This is in the infrared, okay? And infrared gives us a lot of information about carbon type compounds, and so this is a really good place for us to be looking. So this is the little squiggly U down there means micro. So that's micrometers, which is a millionth of a meter. So how long is a meter? About 3 feet, about a yard, right? The yardstick, right? Take that, divide that into 1,000. Yeah, thank you. Right. Yeah, there's always one. There's always one. Take that, divide that up into 1,000, and you've got millimeters, right? That's the little tiny lines on your ruler, right? Take each one of those and divide that up into 1,000, and you got a micrometer. Okay, it's a really tiny thing, right? So this is very, very short. But energy-wise, not so big, right? But this is 7 to 8 microns, and their methane shows up, okay, and shows up quite beautifully. If I look from 8 to 9 micrometers, which is like right next door, right, I get deuterated methane rather. That is methane where one of the hydrogens has been replaced by a deuterium. Deuterium is just heavy hydrogen. It's a hydrogen with a neutron in the nucleus instead of just one proton. And then, so it's a little heavier, so it absorbs a little bit lower in energy. If I go to ethane, it absorbs even lower in energy, around 11 to 13 microns. Hydrogen is a weird thing and absorbs easiest for us to detect, somewhere around 17 to 25 microns. And then I've got the catch-all wavelength over here. This is everything hydrogen or hydrogen carbon related. So hydrogen gas, methane, propane, butane, acetylene, there's acetylene in that atmosphere, okay? 10 to 11 microns. It looks different though, doesn't it? The reason it looks different is because these are all ground-based measurements from the Keck Observatory in Hawaii, okay? This one's from the Spitzer telescope, which was a space telescope that was operational until 2021, 2022, 2021, I think was when Spitzer quit, right? So this is information from a space telescope. So the question is, why? Right? Why a space telescope? I'm glad you asked. Right? This is the reason. Okay. So here's our like we think light. Blue to red, that's a huge range. No, it's a really tiny sliver of the electromagnetic spectrum, right? It's just this little narrow rainbow that I've pasted into this diagram from a textbook. And it's 100% transparent throughout the visible region, which is good, right? I mean, that's why we can see red and blue, because all those colors are coming through. It's perfect, right? But when I get to, if I move in either direction off of that rainbow sliver, I start to see fingers, right? And those fingers reach all the way down to zero or almost zero, right? And every one of those fingers that's dipping down to the bottom of the graph, that's a place where the atmosphere makes us blind. So light coming in from space cannot penetrate the atmosphere at that point because the atmosphere is opaque in those wavelengths. I know we don't ever think of the atmosphere as being opaque because we see through it all the time. But there's a lot of spots in the atmosphere that you just can't pass light through, right? If I get below about 220 nanometers, or below about 220 nanometers, anything higher in energy than that, the atmosphere just becomes a brick wall. And it caused me all kinds of problems when I worked in industry, believe me. And then on the infrared side, it's kind of a picket fence kind of thing, right? So in the I will say the 1980s, but the reality is the first idea for a space telescope went back to 1935. But the first real space telescopes went up in the late 1970s, early 1980s. And I would say continuing to today, although there's a lot less emphasis on space telescopes today than there was before, despite James Webb. And the reason for that is this, okay? So if you look, right, here is that rainbow sliver again. I pasted that into this graph. And you can see there are darn few telescopes that are designed to look into the visible, right? Space telescopes, I don't have to put them in visible. Why would I do that, right? Other than, maybe I got Hubble to give me some really pretty pictures that everybody goes, and all of a sudden you don't mind spending $10 billion for James Webb. But, very few telescopes in the visible. They're all either in the infrared side, where I have trouble seeing, or they're on the ultraviolet and X-ray and cosmic ray side, where again, I can see anything. It's virtually a brick wall, right? Okay. So I put them out in space so that I can see those wavelengths, right? And that's what we did with Spitzer. So Spitzer is right here, and you can see it could see basically from just about right over here, just to the red of our visual perception, down all the way, really down into the microwave. And this was really a groundbreaking telescope. I mean, despite the real fuzzy-looking appearance, that was, people were jumping up and down for joy when they got that telescope. Trust me, it was amazing, right? Since then, we put James Webb up in space, and it covers all the way from just a little bit into the ultraviolet, almost down as far as Spitzer did. So we have both a visual and an infrared telescope in space. And if you want to talk on that sometime, I have a great talk on that too, but not tonight. Going back to this is why we put Spitzer in space, was to be able to see in these kinds of windows where transmission wasn't very good, right? I'm going to blow that region up a little bit. Maybe, yes, I am. Okay. This is essentially 1 micron here. Okay, so 1 micron on the previous graph was right. Oh goodness. Let's see. It's going to be right there. Okay, right at that -6. That's 1 micron. So that first dip at 1 micron right here is the dip that you were seeing on that graph. Okay. And so they've labeled these with letters, right? Because nobody wanted to say from 8 to 11 micron. They just said the K band, right? That's what they did. They named them with letters. But you can see where this, I've superimposed on this graph, where all the things were that we saw in those previous pictures, right? So we've got methane here, okay? We've got deuterated methane here, okay? Here's ethane over here, okay, in this nice open window, right? This one is kind of cloudy, right? But if it wasn't for the fact that methane is really, really prevalent on Neptune, it might be a little tough for us to see it, right? Because it isn't really very transmissive in this particular band. But deuterated methane, pretty decent. Ethane, fine, right? This is hydrogen down here, down in that 20-something micron region. So lots of fingers, but still enough visibility we can see it. Okay. And then here's that Spitzer data right down here in this divot. Okay, that's basically where that is coming from. Just so you know. Okay. There we go. Yeah. So those are what we have here. Okay. So you might ask, I don't remember what's next. Oh yeah, we're back here. So you might ask, what's causing this cloud formation to happen? Why aren't there always clouds? You got methane in the atmosphere. It's there. Why not? Right? And the answer is free radical chemistry. So I was going to bring a demonstration on free radical chemistry, and my wife reminded me that this is a historic building. And perhaps doing a demo with fire was not perhaps the best thing to do in this place. So instead, I bought a video. Okay. No, I'm ahead of myself. Sorry. So this is data from that paper that I was talking about before. So this is a time series essentially of cloud patterns. And you can see there's a lot of variation. The thing that the authors wanted you to notice was that after 2020, the clouds basically fell off to very little, right? Okay, compared to what you had over here in the 2010, 2017, 2002 kind of region. Okay, that was what they wanted you to see in this video. Okay. Shoot, I'm way ahead of myself. Okay, so this is a time series, okay, of cloud brightness. Okay, so that each one of these crosses or dots is a photograph of Neptune. It was taken by either a satellite like Hubble or on the ground from Keck, or there's a couple of other sources as well. And what they basically did here was to just take all of those photos and put them on a time graph, right? So starting in 1994 and ending in 2022. They normalized these so that the amount of the fact that we're on the far side of the sun as opposed to the near side of the sun, you know, all those kinds of variations throughout the year didn't affect the numbers, right? So they took all that out. That's what normalizing basically means. And they took out the background radiation that was that were in the photographs and subtracted that out of the photograph. And so the bottom line here is the time series that they were actually working with. And you can see it's kind of rough, but it's essentially kind of a sinusoidal kind of pattern. When they looked at the time associated with those, they realized it's an 11-year cycle. Just like sunspots. This is weird, right? This is very strange. So how does this work? Now we're at it. Okay, good. So this is the experiment that I actually did research on when I got into teaching in 2004, 20 years ago. And for a while, this was like the #1 hit video on whoosh bobbles on Google. Right? So I think it's just going to run. I don't think it's waiting for me. We'll find out. Maybe I have to click it. Looks like I have to click it. Yes. Okay. So basically what you do is you take some fuel. In this case, it's isopropyl alcohol. Do not do this at home. This has sent people to the hospital because these bottles can blow up, okay, right? So you pour it in, right, and you coat the whole inside of the bottle. You pick up the bottle, you rotate it, you shake it, roll it, roll it, roll it, roll it, roll it, just like I'm doing there, you know, right? And you dump all the alcohol out, right? So all you got is a thin film of alcohol on the inside of the bottle. I make one safety mistake here. I forget to take the beaker of fuel away. But, you know, look past that, right? And what you see is this, okay? And there's a whoop that goes on, right, at the same time. And students, when I do this for my students, they go, oh, yes, right? Yeah. So, yeah. All right. So I also did this in the infrared. It's, by the way, not a heat image. It's just an infrared image. And you can see a lot more of the flame, okay? So what's going on here is that when I burn something like this, I form free radicals, and the free radicals are short-lived intermediates. It's a place where the atoms have split apart, and I have unpaired electrons, okay, which is very unusual in chemistry. And in normal situations, those free radicals last, you know, nanoseconds, microseconds at the longest, okay? But in this bottle, there's not enough air. There's about 20 times more fuel than there is air on a stoichiometric ratio, way too much. And so there's not enough air to take and react those free radicals away. And so these get to sit around and interact with each other for a much longer period of time. Okay? It's called a fuel-rich mixture. Anybody who's worked on carburetors and automobiles knows what a fuel-rich mixture looks like, right? But the interesting thing here is that if I go to the literature before 2020, what you find is that the literature says that there's no point in studying isopropyl alcohol or ethanol or methanol or any of the alcohols because they burn completely to carbon dioxide and water, which is true unless you starve them for air. What we found was this, maybe. There we are. Okay. So the compound that I started with would give me one of these peaks, but it's way back here. I can't see it. I've turned off the detector because it would kill the detector. And then I've made all of this stuff here is all made in the bottle. Right? No additional ingredients, no nothing. I just burned it. That's all I did. And I'm making naphthalene, which is mothballs, right? I'm making anthracene. I'm making fluorine, fluoranthene, pyrene. These are huge fused ring molecules with 4 benzene rings all connected together. This is major synthetic chemistry going on. And all I did was burn the stuff in a bottle, right? It's just amazing, right? 130 chemicals that we could quantify, and we didn't even do them all, right? I mean, just an enormous number of synthetic routes. Okay, all right. This is what's happening on Neptune. The ethane that's in the atmosphere and the acetylene that's in the atmosphere and the larger molecules, and there are larger molecules. There's naphthalene, there's anthracene in the atmosphere. The UV coming from the sun, oh, I gave it a little. There's energy coming in, and it's breaking apart these molecules into little bagel bits, right? And those little bagel bits are finding hydrogen in the atmosphere, which is not hard to do, right? And when they do, they combine, and you get a methane molecule. So the methane is being synthesized by free radical chemistry from the larger, bigger components that are in the atmosphere, okay? This is pretty awesome. And so you ask yourself, where is this energy coming from? And the answer to that question is here. This is the day we did that we had the 3 X-class players, February 24th of this year, right? I'll run this video. I sped it up about 5 times so that it wouldn't take too long. But you can see, right? These are, watch this area right here, right? It just, I mean, it gets so bright that the camera has to turn itself down, right? You know, that's how bright this is. And 3 times it does this, right? This is an enormous amount of ultraviolet energy. If you chart the ultraviolet output of the sun during periods of high solar activity, in other words, lots of sunspots, right? You see that the ultraviolet brightness just soars compared to the times in between the cycles, right? This is major, right? And it's an incredible amount of energy, right? This particular wavelength that you're looking at is the same wavelength that methane absorbs, right around 130 nanometers, which is very high energy for ultraviolet. And that's not the highest energy that got sent in these solar flares. There's energy all the way into the high energy X-rays, right? In fact, that's one of the ways that we chart solar flares in general, is by watching the X-rays, right? So this is like huge, right? And that's what's driving this chemistry. I don't have any oxygen. I need oxygen. All I need is energy to rip those molecules apart so that then they can reassemble, right? Yeah. And so when I look at that and I put the sunspot activity over the top of it, you can see they kind of agree pretty well. The sunspots in gray, right? And the dots are the dots that we saw before. If I change that time series and move it to 2 years forward, right? You get the bottom graph and things line up almost exactly, right? So this cycle of cloud formation is actually dependent almost entirely, right? Dependent on solar activity from the sun. 30 astronomical units away. It's like, God, my goodness, it just blows my mind. You know, thank God for that ozone layer. Keep it up, keep it up. Yeah. Oh man, you know, I don't want to be on Earth 1,000 times more intense, right? That would be terrible, right? Yeah. So this is a major driver, right? Okay. Something else I was going to say there, and I distracted myself. Too much jumping around. Lost it. It's gone.
Right to your,
Yes, thank you. So that's exactly, thank you, a great segue. So the idea here is that the solar flare goes off, bang, right? We're measuring it here. It travels to Neptune speed of light, right? So that's going to be, I don't know. I know to Jupiter, it's like 4.5 hours. So that's 5 astronomical units. So let's figure within 12 hours, the energy from that solar flare has reached Neptune. So that's not the source, right? But what has to happen now is that these things have to get ripped apart. And that takes time, right? And these are multi-molecular reactions. They're happening, and these molecules are colliding with one another, which fragments them even more, right? You've got all this destruction going on, and it takes time for that system to reach equilibrium and then reassemble into the molecules that we see. And that time constant is 2 years, right? So just like, how long does it take for a photon? Anybody know how long it takes for a photon to get from the boundary of the core and the boundary of the radiation layer in the sun? The average photon, single photon, traveling at the speed of light, 11 years. 11 years to go, you know, I don't know the kind of time it takes to get from the sun to Mercury, right? I mean, that's the kind of distance you're talking about. It takes 11 years because it's bouncing around to those. That's what's happening in here, right? You have all this molecular rearrangement that has to occur, and then things have to calm down, right? And it takes 2 years for them to calm down. And that's basically the way it works. We don't know why. I don't know what the reactions are. I don't think anybody knows what the reactions are yet. You know, that'll happen, you know, someday. You know, but that's what has to be occurring. There's just no other real good explanation for how you can have a 2-year lag on an 11-year cycle. You know, but it is so good. And this is, I would also mention, 3 cycles, right? 3 solar cycles. So 3 up and down the sunspot periods, right? And that's it. So, I mean, because we haven't had telescopes in space for much longer than that, right? And we haven't had adaptive optics to telescopes on the ground for much longer than that either, right? And you have to have the adaptive optics to have the angular resolution from the ground to be able to see the clouds. So, which is another great talk, by the way. But someday. But this is, you know, I don't know what else to say. It's just great data. That's what we know so far, right? Now, lots of questions, right? So we have 30 years of cloud data. 30 years is great, except that it's a 165-year cycle, right? So, we've got less than a quarter of Neptune's, year of data here. So, right. I don't know what's going to happen in 40 years, right? It could be a totally different pattern in 40 years. I don't know, right? We have about a 2-year lag between the solar maximum and the peak of cloud formation, and extreme ultraviolet radiation from the sun is causing photochemical reactions in Neptune's stratosphere, which forms the methane, which then condenses at the tropopause, right, at the boundary between the troposphere and the stratosphere. But what happens in the future? I don't know what's going to happen in the future. You can only look backwards, right? In this type of situation, I can predict that this will continue, but I don't know, right? Right. I mentioned the fact that I've got bigger molecules in the atmosphere, right? Part of this free radical reorganization isn't just that it rips apart into small Baco bits and then forms methane, but it also rips it into little small Baco bits and builds bigger molecules, right? Like my experiment did, where I started taking something that's only got 3 carbons in it, and I'm making things that have got 20, 24, 30 carbons inside of them, right? And assembling big molecules. Same thing happens in Neptune's atmosphere. So what happens when they get hit with ultraviolet radiation? Do they break apart? Do they darken? Do they make even bigger molecules, which then typically are very colored? They have, blue and purple and orange and really actually very beautiful colors. But, is that what's going to happen to those things that are on the outside of the atmosphere? Again, we don't know, right? Yeah, more research. Right. So I'm rooting for these guys. They got to keep going, right? That's just the way it is. Okay, and that's all I got. So these are my references. I'll take any questions out there. What do you want to know?
The 2 charts you showed previously, what we were talking about,
Yeah.
is one of them
This one?
lying in the other?
Yes. So this is if I just take the picture data and I put it on the page and superimpose the same solar cycle data from that same date, right? So if there was no lag, if there was no chemical reorganization, and you said this is going to happen on a time scale, kind of like my whoosh bottle did, right? Then these two would line up perfectly, right? As the solar activity went up, right, the clouds would go up, and as the solar activity fell, the clouds would go down. The bottom one is the same data, except that we took the cloud activity, they took the cloud activity, and they moved it by 2 years, so that the peak would superimpose with the peak of the solar activity. And that's how they got the lag. Does that make sense? Okay, right. So I have to say that this is like near and dear to my heart, actually, because when I did my thesis research, that's exactly how I got my fluorescence lifetimes. I created these sine wave patterns, and I just slid them along until they've superimposed with one mathematically, not manually, and until they matched up perfectly, and that's the lifetime just pops out from that, right? And this is the same kind of concept. So how long does it take? What's the time constant? How long does it take for the chemistry to catch up with the energy that's being pounded with, right? And that's basically that's all they did was move the 2 curves relative to one another until the peaks lined up. Okay. Great question. Anything else? Sure.
So are we expecting a lot of cloud formation in the next couple of years?
Yeah, I would say that if this data continues to hold, then what you would see is that the clouds on Neptune would continue to increase for the next 2 years. And then whenever we pass solar maximum, it should start to fall again. There's statistical variation, it's tough to know. That nova goes off in that nearby star system, and then we have cosmic rays coming in, and now you got a whole new energy source. All kinds of weird stuff can happen. But that's what I would kind of expect to see. 2 years, you should see a peak in cloud formation.
Are there any questions from out in the virtual audience? Any questions? One question?
I'm asking now, asking you all. But you're alluding to the fact that you. The days when solar flares occur. Is that correct?
No. Solar flares happen on an 11-year cycle. So they basically follow this sinusoidal pattern of activity. We are nearing the peak of solar activity in this solar cycle. And what will happen is sometime probably late this year, maybe early next year, depending on what happens. You never know what the sun's going to do. It has its own thing, right? And so it's going to go up, and then this number of sunspots is going to peak, and it's going to come back down again. And this happens because of the rotational speed differences between the poles in the sun and the equator in the sun. And what happens is that it warps the magnetic field lines. Right? If you've ever seen one of those or done this in your physics class, they take a magnet and they put a piece of paper over it and they sprinkle some iron filings over it. And you can see all the lines around the magnet, right? That's essentially what magnetic fields around planets and stars actually are like. But that happens because of motion of charged particles inside the sun. So it's a standard kind of electric current kind of generation problem, right? But because the center rotates at such a vastly different speed than the poles do in the sun, you get this formation. If it's rotating this way, you get magnetic field lines that basically have a nose to them because the center is moving so much faster, and eventually they wrap around each other and lap each other, and then the lines start twisting like spaghetti, right? And then what happens is that over a period of time, that evens itself out again, and what was the North Pole flips to the South Pole. What was the South Pole flips to the North Pole. So every 11 years, the magnetic field flips in the sun, right? And this intermediate time, while it's going through that flipping thing, and nobody really knows why that's happening, but that intermediate time is when we see the sunspots and when we get the solar flares that generate this cloud formation.
Thank you very much.
Other questions there?
Thank you.
Where did you say you're teaching at?
I'm teaching at Scott Community College. Yeah. I've taught a few
Teaching
places.
astronomy?
Teaching astronomy and chemistry.
Right.
Yep.
Yeah. I would have preferred chemistry teacher.
I do hear that every now and then. Yeah. All right.
Well, very
Thank you
good.
very much. Thank you very much. Oh, yeah. Sure.
Are there magnetic fields beyond the sun, throughout the solar system?
Yes. So Mercury does not. Mercury cooled off. So the ability to hold on to a magnetic field for a terrestrial planet comes from, it has to still have a molten core. So the core has to have liquid metal in the middle. And if that doesn't happen, then you can't form a magnetic field because you don't have moving charged particles, right? So you have to be a certain size to survive 4.5 billion years and not have your core solidify. So Mercury solidified very quickly. Venus, not so much. Venus does still have a magnetic field, but it comes from a different source than its molten core. We think we don't know that much about Venus, to be honest. We have a very strong magnetic field. Mars has no magnetic field, which is why I no longer has an atmosphere, why I no longer has water, and solar basically blasts that all into the nether regions, and it's gone. Again, because it's smaller, right? It's about 50%, no, 25% of our size.
Yeah, something like
25% smaller than we are, right? I think that's right. And then you get Jupiter. Jupiter has a huge magnetic field. Again, probably for the same reason that the sun does, with a small tweak. Is it okay to talk for a little bit?
Oh, yeah.
Okay. Just, you just can't stop. if I take hydrogen, and I can do this, I can't do this in the lab, but you know, if I worked in a high pressure lab, I could do this. Take hydrogen and you squeeze it, you squeeze it, you squeeze it, keep squeezing it, give it like about, I don't know, 50 times atmospheric pressure or so. And you get the hydrogen to actually turn into a liquid. Which is not surprising. Most gases can do this. This is how we make liquid oxygen and liquid nitrogen and all that one stuff, right? If I continue to squeeze it, however, what happens is that the hydrogen atoms start to orient themselves in space. They're not randomly rolling across each other like marbles in a bag anymore. They organize themselves into structures. And hydrogen becomes a metal, a liquid metal. It conducts electricity. And if I continue to squeeze it, it not only becomes a liquid metal, it becomes superconductive. So there's no resistance to electric flow, right? And when that happens, I can generate huge magnetic fields. This is how we generate the magnetic fields for like MRIs and things like that. We use liquid helium to do that and chill the metal in that wraps the magnet wires until they become superconductors, right? And that means I can pass huge currents with no heating and no resistance, and I generate phenomenal magnetic fields. And that's what Jupiter is doing. Okay. We think. Okay. We haven't done it. Right? Saturn, probably the same thing. Although it's a little murkier with Saturn. Saturn's magnetic field isn't as big as Jupiter's, but it's a lot bigger than ours is. You know, so Jupiter's and the suns are like, you know, the sun, you can say, oh, yeah, this one's bigger, but and Saturn, a little small, right? There are magnetic fields around Neptune and Uranus, okay? But they are tiny, and we don't have any clue where those are. Because no theory we have currently for magnetic field formation is supported in Neptune or Uranus. It doesn't have any of the conditions necessary that we can see anyway for being able to generate field rotation.
In other words, is there any switching of interstellar magnetic field?
Interstellar magnetic fields, not that I know of. You know, but things are weird, you know, I mean, it probably depends on what level of magnetic field you're talking about. When you start talking about 4, 5 light years away to get to the nearest star system, right? That's a long way for a magnetic field to be operated, right? The magnetic field falls off the same way that light does, square the distance. So the farther you are out, you know, exponentially, the magnetic field drops off. So if I had like a nanomagnetic field sensor, could I sense something? Sure, probably. You know, it doesn't just like I'm done. You know, it probably does go on forever. Whether it is a significant factor in anything, I rather doubt it. I think gravity probably is the main interactor between subsystems. You know? So, but again, we don't know. I mean, so where's Voyager 2? It's just outside the solar system, right? That's the farthest we've ever been away from the Earth. Anything that we've ever built, it's the farthest thing we've ever been. Is Voyager 2 launched in the 70s? It took 40 years for it to get to the edge of the solar system. We really don't. I mean, we have some theories about what's out there, and certainly there's some very interesting particle data that's flying in from the Voyager spacecraft. What little we have left because of their power problems. And it's pretty fascinating. So there certainly are charged particles out there. So could you have if you had organized motion, then you could generate a magnetic field. Is there? You don't know. I mean, you know, I don't know that we'll know anytime soon. In fact, you have to actually get a magnetometer out. I'm there here.
Yeah, thank you very much, Dr. Gregory. That
Yeah.
really, okay, yeah. which is sharing there. Really did well to tie together what we've seen this afternoon. I know some of you looked through our hydrogen alpha scopes and saw the solar flares, result of some of the magnetic disturbances on the sun. We know what happens now when some of that gets out as far as Neptune. And,
Just bought that picture. It's over here.
I'm over it.
okay, we appreciate the
It's nice to do.
it's a pretty well. It's probably well.
Thank you very much.
Thank you very much for your presentation. Let's see. You have some mini tool partition wizard trying to update. I will close out of that. I don't think we need to update anything right now. Okay, where did mine go here? Need to go here and, okay, here we are. Okay. Okay, we're going to move on to some of our member observations, and my folder, I think I have to go back to where I can get to that here, and a few views. Well, no, not there. Oh, okay, I gotta need to go down here to the share and go this one, and I gotta click on share down here now. Okay, this is what was going on today, and if I, there we can see. We had quite a group this afternoon at the Moline Public Library. And, oh, okay, this, I think I need to go back to my screen so I can share the different views we have here. Okay. We actually counted over 400 people there. We estimate there are certainly around 500 people, maybe even more there today. Few more views of the large groups we had. We had 10 telescopes from the Popular Astronomy Club there today. The view of the people. These are this is the big lineup waiting to see through the hydrogen alpha scope that Al had set up today. More groups, people looking up I think this one was near the maximum eclipse. Oh yeah, okay, I see what I did. Some more out here. There's Rolly with his scope, showing it off. Oh, okay, these things keep jumping around, don't they? And we have okay, Waylon, there you are. Waylon had a hydrogen alpha there too, looking good. Oh, that one? That was yours, wasn't it, Rusty? That was Rusty's hydrogen alpha there. Okay, and there's Eva checking in some of the people as they got their eclipse glasses and registered for the group. So, Al, I think you have some of your screenshots on here too. So I think I can just minimize this, and you'll be able to go on to yours here, I think.
Yeah. Let me see if I can.
Okay, I see what happened here. Mine, I should have closed these out. Yeah, instead of just sharing the individual ones, I was just opening all of them. So, That will leave most of the screen there for you to find yours.
Yeah, I gotta find mine now.
Yeah.
I think it's,
I think you minimize.
I think it's right here.
Yeah, okay, there
Yeah.
you got it. Hiding behind my PowerPoint.
So, all right, well, we'll start with this one, I guess.
That's the good one.
Now, this picture was taken through the PACMO 12-inch LX200. And that was taken at 1:55 PM. So it wasn't the deepest part of the eclipse, but it was close.
That was very close, yes.
And by that time, it was obvious to anybody that was paying attention that there was something going on, weird, with the sun. And we were only receiving, at that point, we were only receiving about 10% of the sun's energy at that point. So can you realize, and you could feel the temperature had dropped. And so imagine if our sun lost that much energy to space and we didn't receive it. It would not be very long before we were froze solid. But it was also amazing that, you know, even at 10% of the energy, how much you could still see. It was still daylight. And so a lot of these pictures were taken right at that time. Let me see here. The problem here is, yeah, see, the problem here is I'd like to get this out of here. How do you get that? So you want to be able to use the controls over here, but you can't do it.
Yeah, that's what I thought would work with mine, but it's not doing that.
All right, well, we'll do it. We'll do it one at a time.
Yeah, that's what I had to do.
We'll skip that one. That was a mistake.
Well, let's see, you skip your mistakes.
Yeah, well, hey, I'm doing the presentation. I can skip the mistakes.
Pretty good feature we got on this computer.
Some of these pictures are the same, maybe as what you had, is taken with a different camera. But we had a lot of people there and there was a lot of interest. There was a lot of really good questions.
Are you gonna have that picture in the newsletter later?
I assume so.
These will go to our newsletter editor, who's actually off. He missed it. He's off in Australia right now. So, but he will be able to choose the best ones, put them in our newsletter.
Where would you at? The middle.
You did run
Let's see if we can identify. Okay, so I think that's Dan. Let's see, who else can you identify here? I think most of the people in business, so that's Dan, and I think that's his also there. And that was that Dan's also? Yeah, the family also, yeah.
Yeah.
So there's two telescopes right there. And
I'll walk through. I counted 10 telescopes. So I counted yours as double because you have both.
there's some scopes back there. I think I got pictures of those too. That might be. Oh, is that, where's Rolando? Oh, yeah, yeah. He's hiding. He's hiding. He doesn't like to. I guess Rolando doesn't like to have his picture taken. Yeah, right there. See, I try to get your picture and then you cover your face.
Oh.
So, what telescope did you have?
I just had the one.
You had a Lunt, so it's an H alpha. The H alpha really was, really spectacular today.
Yeah, it's nice that we had a flare you could observe.
Now, Dale, I think this is your setup, right?
Yes, it is. That's the lead 7-inch.
And then you had another scope over here too, right?
Yeah, I had some difficulty with that one.
getting set up, so I didn't really use that very much.
There's always good reason for having two telescopes, right?
Yes.
One will malfunction.
The Meade was set up, a lot of people, like seeing that, I had a little bit closer view, so I could see actually the point there with the sun looked just like a crescent, could see the point of the crescent. So a little bit of variation there along, I suppose it was just some of the mountains and hills on the moon that caused a little bit of variation. Either that, or I just didn't have a perfect focus on it to see the line between the moon's shadow and
Yeah,
the
but
actual
this,
sun.
but the story is that there's craters and mountains on the moon.
That's what it's supposed to be anyway.
Yeah. And that's Whalen. And Whalen had a nice setup there with his scope, and he found a good eyepiece for it as well. That's a white light filter. And let's see. And that's Rusty. Right there. And that's John Douglas.
You're still on Wayland.
Just can't get rid of me.
We lost connection there for a second.
Well, looks like we did.
Yeah, we had the network.
Yeah.
We broke it. Okay, so what do I want to share, right?
Yeah,
I don't know what happened there.
somehow your sharing, we got lost. Oh, you're back.
Okay, all right. Let's see. I think we're here.
There's Rusty.
There's Rusty. Rusty had an H alpha. Go over here.
Yeah,
And then you had your 11-inch
yeah.
Smith Cassidy in there. with
Yep.
the solar
The East
filter.
Alpha was a big hit.
Mhm.
That was getting, everybody loved that, loved the red,
Mhm.
taking pictures. And then they were struggling trying to take pictures through the eyepiece of my 11-inch. And one guy decided to use the finder scope and got a really nice picture of it, so.
Oh, through the yeah.
Finder scope.
Well, the nice thing with the sun is you don't need a big telescope to look at the sun.
Yeah.
Even a finder scope's enough magnification. But people are still impressed with big aperture telescopes.
Oh, yeah, it looks impressive.
That's why the line's so long.
Yeah.
There's a nice shot of your H alpha.
Yeah. Yeah, it was only 35 millimeters, but it does.
Yeah. And
For the sun, it does the job.
yeah, the main thing, and that's 10% illumination. That's 10%
Mhm.
illumination. If it was 100%, I don't know if I could really tell the difference, but you could tell when you were out there. It was different. It seemed things were weird.
Well, people come tell me they're cold, I didn't see it, but I was in it down and then protected and I was on the black shirt, but really, it's not getting cold. I couldn't think of it.
Okay, okay, that's you, Dale, and your two scopes that we had.
Okay, yeah.
So how many scopes did we have? 10?
I counted 10. Counting yours is 2.
Yeah,
I had two.
Yeah, I counted both of yours.
that's the same thing again, I guess. Now we got Rolando there. And Dan, Dale. Oh, yeah, that little girl was looking in there.
Oh, yeah.
There was a lot of kids there.
Yeah, there
I
were.
had one little girl was looking through the H alpha and I said, did you see it? She goes, yeah, looks like a cherry with a bite on it. So I had her look in the 11-inch and I said, what do you think of that one? An orange? She goes, yep, that's an orange with a bite on it.
And then this is what we had with the mobile observatory, and Pam was operating the scope at that point and talking to guests, and Eva was here at the table. Yeah.
Mhm.
And
That was at the end of the day.
Those, yeah. Oh, there's Pam looking through the scope. And you can see here's our H alpha that we have. And actually the H alpha scope was one that the club purchased from Wayland. This is yours. Originally it was yours, Wayland. And that really is a nice scope. Yeah.
They were a real big hit.
Yeah, those were too nice to have a mounted on your scope there, so.
Yeah. So you can look at,
Use.
it's a little bit tough to get everything balanced just right, because that's a lot of weight, you know, this telescope is 80 pounds, and then you put something that's probably another 15 pounds or so on top of that, and then it's really top heavy, and then you got to put a bunch of counterweights on it.
Yeah.
But it worked. Yeah. And this was inside the library. That's my wife, Sarah. She was, she handled the table inside.
That she gave out more packaging than she ever had before.
Yeah.
There was a lot of excitement.
Well, I ran out of the first box she gave me and she brought me more, so yeah, we gave away a lot of stuff.
And so,
Yeah, we went over about one.
Oh, okay.
yeah. So there's the sun. There were actually some nice sunspots, but I didn't get a picture of that. The people kept coming around to the telescope and wanting to use their cell phones, and once in a while you could get a picture, but most of the time you can't.
Actually, probably about 20 to 25% of everybody that tried on the
Yeah.
telescope couldn't get a picture. But we had one guy, or one little girl was over there with her cell phone on the H alpha and got this fantastic picture. And so everybody's hands are.
The guy who had the camera that you looked up, was he gonna send you pictures?
I asked him, I gave him a card. He's gonna send that picture too. Yeah, he was. I'll have to check here, but this was, you know, finally, I just said, look, everybody, I'm gonna take a picture. And then, you know, just chill out, you know, about the cell phones, because they don't work.
Well, that's when I got the card to the Iron Club, I was meeting them before them, so that I could get people more information.
You gave out quite a few cards.
I gave out quite a few, there's not a lot left.
Donations?
No, no, 100 and something.
Yeah.
It was 100, I don't know, it was over $100.
Yeah.
Which was great.
It's in our donation box and on the table.
Because
So-
everybody thought they got how much less.
Yeah. Any other observations?
Any other
Anybody?
observations? Did we have anything online? A brief report on locality? Yes, we do.
Did you send a picture by email?
Yes.
Wait, I can probably find it. Well,
Cause all I had was my iPhone and
Mhm.
it wasn't the optimum conditions.
is that this here?
No, that's with telling you about the trip.
Oh,
It would have came today.
it did not come before I left. to
Oh,
come
maybe
here.
it was too big.
So,
Did you see it? Did you see it? Are you-
I thought,
Well, they aren't that good anyway, so I can just relay
okay,
my experience. I had the opportunity, I had the opportunity with 3 other guys to fly down to Mount Vernon Airport today to watch the totality. And for all 3 of the other guys, it was their first experience, which is something that'll lead to something else here. But it was fun. We were on the airport. There were about 50 other airplanes that were there. And basically what happened was when it got to around 50%, you could sort of feel the temperature go down, and you could tell on the concrete, you weren't seeing the sun reflecting on the concrete. The concrete started getting darker. But otherwise, looking around, you don't really see a whole lot going on. But finally, when it gets down to Al's picture of the 90%, when it gets there, you still see a lot. The lights start wanting to come on. The runway lights came on. They thought it was getting dark. And if you look to the southwest, you thought a thunderstorm was coming, because you're seeing the hole coming at you. and you swear it's a thunderstorm. It looked just like it. And finally, when it got down to less than half of what that picture shows, you still could see pretty good. It doesn't take much sunlight to illuminate things. And so that's why when you're up here at 90%, you're saying, what happened? You know, unless you're looking through. So then when it went to totality, and we had 3 minutes and 45 seconds down there, so that was kind of neat. That was long. Mount Vernon. Which is pretty much right in the middle of the path, and that was neat. There was no diamond ring at the beginning, which I thought it usually was at both ends of it, but didn't see anything at the beginning. However, when you look on the internet or on TV, whatever, you'll see on the bottom of the sun, there's a pretty large prominence, and you can see it with the naked eye, hanging down. And then I had my 25 by 100 binoculars. And looking with those, you could just see flares around the right side of the sun just going crazy. It was just jumping out like crazy.
I
I
saw
didn't
them.
see any bending of the light of a star behind the sun like Einstein predicted. But
That's what we're looking.
yes, but do you see is it bright at the bottom? Is that from today?
Yeah.
Is there
This is Liz and Brad. We're in, we went to reality.
They're getting all kind of, yeah. But if you look on, when you see the pictures of it, you're gonna see a light. That's not the diamond ring. That's a prominence coming out of the sun at the bottom.
We saw those.
Well, then when it ended and the moon moved out, huge diamond ring. And you could hear, it was like fireworks, people going, oh, that was neat. It was just a big one. It was wonderful. And so the 3 guys I was with, they said, oh, now I understand why people say, I just can't describe it to you. You know, you've got to experience it. So if you ever get the opportunity to do a totality, it's something to see. So that was my experience. So I don't have any fancy pictures or anything, but it was quite the experience. All right.
Very good. Hopefully we'll get an opportunity, but I think we have to wait a few years at least around this country. And that's only going to be at the northern edge of the lower 48 states. There's some other opportunities coming up in a few years and in 10 years or so. Europe, Africa, there was a list online of where all the future ones are coming from.
I think I'm in the wrong place.
Oh, yeah, we don't need to.
You got a picture of that. That's pretty cool.
Just a minute. Here he is.
Yeah.
Okay.
So that's Ross' picture.
Yeah.
That's pretty decent.
Yeah.
And Roy, did he say where he was?
Yeah.
Harper,
Harper,
Texas.
Texas. Okay. Yeah.
He says it was 4 minutes and 22 seconds. And it wasn't too cloudy, so.
Well, he's fortunate because I did hear a report that some of the areas in Texas that people went to had some clouds today. We still got to see a lot of it, but it was partly cloudy.
Yeah, there we go. I was in the wrong.
I think we
place.
found yours, Mike.
Well, but it definitely shows the moon.
You can
biting
see the
into
bite
it.
out of the sun.
Whose pictures are those?
These came from Mike.
We're probably approaching 90% there.
Yeah.
Yeah, it looks like about that percentage.
Yeah.
So we can see somebody else.
Paper, I took the
Oh,
filter
yeah.
off, and then using the binoculars.
Mm-hmm.
Can't take it on a piece of paper.
Nice.
I unmuted.
Totality at the end there. Yeah, you might go see that at the very bottom, well, it doesn't show up too well. You know, it doesn't work out.
Well, it
Oh, yeah.
definitely shows the,
Yeah,
What's-
actually see it better there on the big screen there.
Just show us.
The flare coming out the bottom there.
oh, yeah,
Mhm.
yeah.
I tried.
Do we have any others here?
Ah, I think from Roy, from Mike.
That's the same one from Roy, I think,
Okay.
3167. Chad Potter gave us a report from
Yeah.
John Deere Middle School. He said everything went really well
That
there.
was on the
That was
news
on
this
the news
afternoon too.
Yeah.
Yeah, they have pictures on Facebook as well.
Okay.
So this eclipse is the biggest thing today.
Yeah.
I mean, that's the big news item. And there were not a lot of discussions about political problems.
Yeah, to have more eclipses, that would make the news better.
That's right.
That would be a big improvement. Yeah, Mike.
We were down there in 2017 and leaving the eclipse, the interstate was more like a parking lot than it was an interstate.
Mhm.
Cars were police were there directing traffic on the ramps, so crazy. Now, in August of 17, it was on a Sunday.
Mhm.
When we flew out, you couldn't tell anything on the interstates if there was anything going on. So being a weekday.
Yeah.
I'm sure
It's
the
a
crowd,
difference.
I'm not sure what you saw numbers different at the library on a weekday compared to on a Sunday.
It was a pretty big
Yeah.
event for us. What did we say, 500?
Yeah.
It was about 500. It was over 1,000 when we were there in 2017.
Yeah.
Sure.
1,500.
I thought the same thing on the highways.
Yeah.
Did
But-
anybody else notice when you're crossing the I-74 bridge that it has a sign that says do not stop for the ambulance?
Oh.
I thought that was hysterical.
Should have got a picture of that.
Well, when I was going home, there was stop traffic on the I-80 bridge, but that was because of the construction. I don't think they were looking at the eclipse then.
And one entrance had a sign that said, it is illegal to stop on the road or on the shoulders.
yeah.
On the shoulders of the eclipse.
Yeah.
It was-
Okay.
Yeah.
Okay, I should be able to get back to, okay, here we go. And I think we've seen all our observations here, so here we go. Talking about what's coming up now in the future here. Of course, Niabi Zoo, we're coming up there April 20th. WQPT, as it did last year, this year they've asked us to provide observing at their annual gala program. So we will be going out there and helping them with that. Again, the Giant Goose Campground Youth Day, solar viewing on June 1st. We'll be going back to Eldridge Library again this year. That's always a big program that we have, June 24th this year. Messiah Lutheran Church out in Port Byron has asked to have a vacation Bible school evening observing program on June 25th. So, and that will be open not just to the vacation Bible school, but to the public there and church members in Port Byron. Also up that way, the Elina Wick Campground, one of our biggest and most popular programs of the year, will be on June 29th again. Brian Fox Ellis at Bishop Hill has asked us to come out again this year. They
So can
play
I.
around at Bishop Hill trying to decide just when to have their program, and I haven't heard back confirmation on that one yet, so that's still to be determined. Silvis Library has been waiting a couple of years for us to come out to their centennial celebration there with an observing session on July 11th. Muscatine Library and Muscatine County Conservation District has asked us to do program. I've given the information back to both of them. I don't know if we'll be able to combine those or we'll have a couple programs out in the Muscatine area. If we go out to Salisbury Bridge, that will probably be one of the most distant programs we do. So we don't know if we're going to take the PACMO there, how big that might be yet. Back in the Port Byron area, we'll have another, this will be, I guess, the third annual Riverdale School observing session. Putnam Museum has asked us to participate this year in an observing program at the museum. We don't have any details about that. Bettendorf Girl Scouts again has asked us to provide a program for them, date to be determined. And the information of what we did out at the Loud Thunder Observatory has gotten around to the Boy Scout Iowa Conference. They have asked if we'd be interested in doing an astronomy talk about some of the merit badge topics. So I think we'll probably see what the schedule is and if we can do that this year. So we have a lot of things coming up for the rest of the year. Our meetings here next month, May 13th, have Dave Weinrich, who will be presenting a program, Keep Looking Up, One Sky, One World. Should be an interesting program about astronomy, amateur astronomy around the world. Our picnic's coming up on August 10th, which will be the weekend closest to the Perseid meteor shower. And our annual banquet is confirmed for October 12th. Other things we are doing, April 22nd, some of us, including Roy, will be presenting the library telescope, which we talked about in past meetings here, to the Orion Library. That's at the night of their board meeting. We have the regional conferences coming up, NACRL in De Pere, Wisconsin. There's a website, you can already make reservations for that coming up very soon here. And June 7th through 9th, the Mid-States region, be at a state park near Omaha. And we have, okay. They said the schedule is not yet available. Maybe by next month we'll know what their schedule and what their talks are going to be at that. Alcon coming up July 17th through 20th in the Kansas City area. They have 9 speakers listed on their website, but they didn't have a schedule yet of when each speakers are happening or the actual times for the various programs. So you can look online and get the information on most of these. Okay. By the end of May, we need to turn in our membership to the Astronomical League for our official annual membership totals. So if you have not renewed yet, please do so soon or you will not be included as a member anymore. We had the Skywatch article. This was the one written by Al, which appeared a week ago in the local newspapers, and a very good article about the eclipse that's coming to the Quad Cities. We need some people to write some articles for the future here. So if you feel like sharing some of your astronomy information with the local public in the newspaper, here's your big chance to get your article published. So, do we have anything else to come up tonight? Come back here next month, May 13th, for our next meeting. And until then, keep looking up. Thank you all for coming tonight.
Very nice.